Hello everyone and welcome to another class of ATMO 620. We are almost at the end of our lecture series. Still talking about radiation. Today we will talk about heating rates. What does that mean? Well, electromagnetic radiation goes through the atmosphere, either emitted from the sun or from the surface of the planet. This is absorbed in the atmosphere, and this causes some cooling, some cooling and some heating, okay? And today we'll talk about that a little bit more. Okay, so let's get right into it, and we will start by considering a slab of atmosphere of a given area. Okay, we'll call the area A, and let's say that the slab has a particular thickness delta Z, okay? As usual, we will make plane parallel atmosphere assumption. So the atmosphere is homogeneous horizontally, and we'll mostly consider like going either up or down, kind of in a straight path. Okay. Now, if you have this particular slab, it's delta Z. There's some radiation that is entering at the bottom, some that is emerging at the top, and in particular, there will be some net power that is delivered on this interface here, okay? And the power will be AFZ, where FZ is the net irradiance at the bottom of this, and A times FZ Z plus delta Z is the net power at the second interface, okay? So the power that is lost within this layer, okay, is the difference of the net irradiances between the two, okay? So very simply, for delta Z, very, very small. This is kind of, goes without saying. I mean, you can, by definition of derivative, or you could Taylor expand this to the first order. This is simply A times delta Z, which is kind of this volume that you're considering, times the vertical derivative of Fz, okay, where Fz is the net irradiance in this case, okay? Okay, so this quantity, this power that is lost, okay, it's lost to the gas, and it is delivered to, it causes a heating of this slab of the atmosphere, and the heating is proportional to the power that is lost within this layer, okay? So the net diabatic heating, notice the diabatic and not adiabatic, the diabatic heating that happens here is precisely equal to dFZ over dZ, and it's weighted by the density of the atmosphere, which kind of makes sense. If there's less, if the atmosphere is less dense, then there is different amount of heating than when it is more dense. Okay, just because there's more atoms on which scattering can happen. Q, this function, this quantity here, is given in watts per kilogram. Okay, and you can also rewrite if you normalize Q by Q by the specific heat at constant pressure, Cp. This as the units of Kelvin per seconds or Kelvin per day, which is often the units or measurements that these are given in. Okay. So in the case of, this could be, for example, this heating could be due to shortwave. We have diabatic heating rates per unit volume. These would simply be some Q that is given by absorption of shortwave photons that are coming in from the sun. Okay, if you assume that the sun is directly overhead, you neglect scattering for simplicity. You can also define This is something similar to optical path but it's called optical depth. Optical depth is different only because it starts from infinity and it goes to the point Z, okay? But it's essentially, well, sorry, this is from the top of the atmosphere to infinity, okay? But it's essentially the same quantity as we had defined before. It's sort of more used in the study of atmospheric phenomena. So with all these assumptions, you remember the Baer-Lambert law, the downward solar irradiance is given by the downward irradiance that you had at infinity, so the one that had just left the sun. Also assume that there's no interactions with the sun's atmosphere and the corona and whatever, times e to the minus optical depth. Okay, and this, by now, this should be pretty intuitive. Okay, this is the incoming at the top of the atmosphere, or even like, you know, empty space, whatever you might want to call it, and this is at some point Z within the atmosphere. Okay, we are neglecting scattering, however, and so the upward solar irradiance must be zero, right? Because there's no shortwave heating that is caused by the surface of the Earth, okay? And therefore there is no backscattering. There's no, sorry, there can be, you know, any kind of scattering or any emissions from the surface of the Earth. And so the downward solar irradiance is also corresponds to the net solar irradiance, okay? And this is simply a function of, as we said above here, simply a function of the downward irradiance at the top of the atmosphere times this kind of extinction term due to, that is proportional to the optical depth. Okay, now, so what is the heating rate? Well, the heating rate is simply given. Let's just get rid of the density and multiply it in front here. The density times heating rate, it's simply the derivative of the net irradiance, which was this constant term, which we can, you know, very simply get rid of, and, well, take out of the derivative, times the derivative of e to the minus chi nu. Now, the derivative over z of e to the minus chi nu, okay, this would be simply e to the minus chi nu, okay, z, because this is an exponential, but also the derivative of chi nu with respect to z. This is the law of derivation of composite functions, okay? The derivative of d chi nu, remember the definition of optical depth that we gave somewhere here. So if you take the derivative of this, it's simply k nu times rho of A. Okay, so let's go back to this. This is simply k nu rho A e to the minus chi nu. So substitute everything. And this is simply giving you the heating rate. Okay, now we can assume, just to get some kind of an idea, we can assume that k nu is independent of height. We can assume that rho A has an exponential function like e to the minus z over h, where h is some kind of a scale height. And then the optical depth is then going to be some constant times this exponential, okay? We can do all the calculations and we would find that. Next slide. We would find that the vertical irradiance would then be given by this simple expression. Notice that it's an exponential of an exponential, okay? So put everything in the machine, compute yada, yada, yada. The heating rate due to shortwave radiation is this complicated expression. You can plug it in a computer and plot this function here, okay? Notice a couple of things. Notice that this function has a maximum at about the scale height that I had defined here, which also corresponds to optical depth being equal to 1. It is lower above and is lower downward. Now, why is that? Well, this kind of makes sense because look at what this looks like. Look at this expression. If you go higher up in the atmosphere, okay, then there is less gas, less atmosphere to give heating to. Okay, so it kind of makes sense that the heating rate decreases. But if you go down, now you have absorbed a lot of photons. Many photons have been absorbed here, and so there's fewer photons to deliver the heating. And so the heating decreases here because there's less photons. And so there's like a sweet spot here where you have the right density, and also you still have enough radiation left to deliver, all the heat that you need. Okay. A structure like this is known as a Chapman layer. Okay, and yes, just keep in mind for sort of nomenclature. And this slide just said what I just said. So here we are exactly in the right spot. Okay. Okay. So let me just drink. In terms of long wave heating, on the other hand, well, long wave is slightly more complicated because now we can have some photons are contributing to the upward direction, okay, and some are contributing to the lower direction, okay, so sort of directed, sort of scattered back, if you will, okay, and this is simply another way of writing the solution to the Schwarzschild's equation, if you will. Remember that transmittance was related to the optical path, right? And also, if you remember, we had said that both the source function here and what is emitted at the surface of the planet, this was the Planck's function, okay? The Planck function here I'm showing as a function of height, not so much as a function of temperature, right? So this would be at the temperature of the surface, okay? And so this would be the source term for the surface of the planet. There is something that is emitted here. You are at an altitude z, okay? So b nu, pi b nu is emitted here, and by the time you get here, some will have been absorbed, and this is accounted for by this transmittance term, which is nothing but e to the minus optical path, okay? If you remember, the source function we said was equal to the Planck's function under assumption of local thermodynamic equilibrium. So that's what we're also assuming here. And plus, we also have this term, which is the source function at different heights. So we're summing over what is kind of re-emitted at different heights, and that contributes to what is emitted at different heights and contributes to this at z. And the downward, so this accounts for the upward directed long wave radiation. For the downward directed long wave radiation is kind of the same, if you will, okay? Except that we don't have a source term, because the only source that we have in this process is the surface of the planet, and this is only giving radiation that is going up. There's no other boundary that is giving radiation that is going down. So we have these two terms, okay? And we can proceed and we can compute the difference between the two. This would be the net spectral irradiance would be the difference between the two. And from this, we can then compute the net heating or cooling rate at a particular altitude, okay? Okay, so this is, let me just check. Yeah, I'm not sure. Okay, yeah, we'll talk about this later on. But anyway, so with this equation, we can then start to compute sort of heating and cooling terms directly, right? In terms of the long wave radiation. Notice that in this case, we are assuming that these are photons that are emitted from the surface of the Earth. They're emitted upward, and this is essentially energy that is lost to space. Okay, and so these are sort of cooling to space terms, if you will. Okay, this is just to remind everybody that under local thermodynamic equilibrium we had this, and that's why we wrote the source function as a Planck's function. And with all these assumptions, you can do all the complicated calculations, and what you end up at the end would be something that looks like this. Okay, the heating would be essentially the Planck's function times the vertical derivative of the transmittance. Okay, so still a pretty simple term, although you don't know how complicated this is going to be, and this is actually quite a complicated piece. But both the short wave and the long wave heating terms can be computed very simply. Sometimes, so this can be particularly the long wave cooling to space term. It can be a pretty complicated term. And so sometimes it's not uncommon to use very simple assumption and just call use what is known as a cooling to space approximation, and just essentially assume that the loss of photons to space dominate all the other contributions, because you could have one slab of the atmosphere being influenced by other slabs of the atmosphere, and this would make it really complicated, because in order to know what's happening in a particular point, you have to know what is being emitted by all the different points, and these are kind of interacting with each other, and it would get really complicated really quickly. Just assume that what is lost by the slab to space is the dominant source of cooling, if you will, and that dominates everything else. Okay, so we introduced some formula to describe the heating due to short wave and the heating or cooling due to long wave. But what do they actually look like? If we were looking at heating or cooling rates, what do they look like? And this picture shows different cooling rates or heating rates due to either short wave or long wave. Okay, short wave heating and long wave cooling. Okay, and so notice a few things. First of all, a lot of the cooling, this would be sort of your Chapman layer structure. A lot of the cooling and the heating happens really, really high in the atmosphere, at about 50 kilometers high in the atmosphere. Okay, and there's also a lot of heating above the and above the Kármán line. Okay, so above 100 kilometers. Relatively little happens in the lower stratosphere and in the troposphere, luckily. Notice that the main responsibles for the heating and the cooling that takes place in the bottom of the atmosphere are water vapor, more or less. And there's a little bit of contribution from ozone and CO2, but it's really, really minimal. What really matters a lot is water vapor that kind of dominates heating and cooling. Notice also that ozone here is the dominant heating term here in the mid-stratosphere. Okay, it accounts for almost all of it, and oxygen then sort of takes over at greater altitudes. Notice that these terms almost cancel each other perfectly, so that there's almost a perfect radiative balance between the two. One of the few places, well, the only two exceptions are above roughly 90 kilometers, where this balance is broken, and below roughly 18 kilometers. So in the troposphere, And so this radiative equilibrium holds well pretty much, everywhere in these layers, but not here on the surface. And this is kind of lucky, if you will, because this is what gives us a lot of the weather. So yeah, as we were saying, the heating due to ozone and oxygen is really, really important higher up in the atmosphere. And this is the Chapman structure that I mentioned before, centered at about 50 kilometers, almost entirely due to ozone, which again underscores the importance of having ozone in the atmosphere. Okay, and water vapor is the most important contributor in the troposphere. What else? What else could we say? CO2 is important, not so much for shortwave heating, but for cooling in the long wave, and particularly in the stratosphere. And the wavelengths that are involved in this are if you remember the spectra for this, are the 15 micrometer for the CO2 and about 9.6 micrometers for ozone. Okay. And if you have to keep in mind a particular quantity, a number, then in the troposphere, if you sum these two, this is roughly equivalent to a cooling of 2 Kelvin per day. The units are being cut out for some weird reason. This is Kelvin per day. Okay, and this is a standard kind of approximation that sometimes people use. If you don't want to care about particular complicated processes that happen in the troposphere, to say, hey, constant cooling term 2 Kelvin per day. Okay, obviously this would be highly dependent upon latitude, season, clouds, part of the planet where you are, etc., etc. But for now, we can just simply assume that on average, that will be sort of a 2 Kelvin per day, and this very nice radiative equilibrium it holds statistically, but not necessarily at every particular point. But this is kind of interesting, though, that there is this equilibrium, because essentially it means that nothing else has to happen. Like, it almost seems like the stratosphere is kind of happy to be what it is. Whereas the troposphere is always looking for, convection to adjust something, to reach some kind of equilibrium that needs to be reached, except that it's never reached, and that's why we have weather every day. The last thing I wanted to say is that Newton had come out with a very, very simple way of writing down sort of the cooling of the atmosphere. And particular, if you suppose that you are at equilibrium at a particular point, so that the net heating at a given temperature is 0. Suppose that you heat up the atmosphere a little bit. Okay, what does the heating looks like? Suppose that you have Q of T plus dt. Well, this you can expand with a Taylor expansion. Okay, this would be QT of R. Okay, this T of R is the equilibrium, plus dt times dq dt. This is computed at T equal TR. Okay. But Q at TR is equilibrium, so by definition, this is 0. And so you're left with this term. And this can be rewritten in terms of the heat capacity times the temperature deviation over some time scale. Okay, and the time scale can be computed in terms of dq or dt, okay? And so you can assume, suppose that you heat up a little bit and you deviate away from this perfect equilibrium, you could always assume that for small enough variations, the heating that is given is proportional to the temperature deviation times some kind of a time scale that you can always estimate it. This time scale is known as the radiative relaxation times. Okay, and this is sometimes used. It's called Newtonian cooling approximation. It's sometimes used when you do a calculation of the atmosphere. Okay, this was pretty much all I had to say about heating rates. And as usual, for questions, feel free to get in touch. Let me know. And I'll be more than happy to explain anything or to discuss anything that was not clear. Otherwise, I will see you for our next class. Thank you so much for listening.